Okay, part 3 for chapter 19 is just going to be a very short video on hybrid parameters. And it really shows that, I'm going to show that hybrid is really just the general form, and the impedance and admittance are a particular orientation of the hybrid parameters. So that's what we're doing here. And let me just refresh. So we have our networks, right? And we simply said that we have a network port that is a single port, and then a two-port network just simply puts two ports on some network. This doesn't imply that there's a voltage source here or here. There might be one. There might be both. Okay? You don't know. But so this is the network. What's important here that I'm getting at is it's defined in terms of four variables: the input currents and the voltages across the two terminals at what I will call input on the left and output on the right. There's nothing magic about that assignment. It's just a left-right way of talking about it. Okay, and so far we've had two types, impedance and admittance parameters. They're parameters of what? We're just trying to describe, we want some way to describe what's going on in this circuit as seen at the ports. Right, so this is our eye here at the ports looking in. And likewise over here, we're looking in and we're really just seeing, we're seeing something. Okay, and this is one way, one of several ways of describing what we're seeing. And we chose to call them Z parameters because we're familiar with the simple relationship impedance is voltage divided by current. And in the case of parameters, we're saying it's voltage divided by current under some condition. All right? And we defined a condition under which we can find each of these four parameters, Z11, Z12. And the way we find that, of course, is to somehow take this first equation, if we want Z11, and somehow eliminate this. Right? Well, we can do that if we make the condition. So I can find Z11 is V1 divided by I1, whoops, if the condition is that I2 equals 0. Okay, and we get that by being an open circuit. Okay, so I'm not going to go through them all like that, but quite simply, what we did was we said I have four terminal parameters, voltage and current on one side, voltage and current on the other side, and I can arbitrarily choose to relate those any way I want. Okay, let me say that again. I can arbitrarily choose to relate input voltage and current to output voltage and current, or current and voltage, in any way that I want. Okay? This is one way. The impedance is one of those ways, where I make the voltages a function of the two currents according to some parameter which has the units of ohms, which has the characteristic of impedance. Okay? And then that nicely lines up as a matrix combination here, a matrix picture. Okay? Then we went on and did the same thing with, and we called them admittance, only look, all we did was decide I'm going to make the current values some function of the voltage. Okay, the voltages. I arbitrarily chose to do it this way. And when I do, I get y11, or y, is equal to, what have I got? I1, I over V, under some condition. Okay? And I over V turns out to be the inverse of impedance, so we call it admittance. All right? And to make calculations and determinations easy, we set the condition to V equals 0. And so if we're looking for y11, we want it to be I1 divided by V1 when V2 is 0. Okay? So all of this was done, and once again we wind up with these very nice matrix forms. Okay? Now I want to emphasize again, all of that was done simply by choice. There was no built-in math that said it has to be this way. This was all choice. I wanted to write two equations in four unknowns. Okay? And then depending upon what sources I have or what I know, I might have dependent and independent variables here. Okay, so we started this chapter with these definitions, impedance and admittance. Okay? It turns out, obviously, saying these things are arbitrary, we could actually pick what we got several ways we can assign things. We can have V1 and V2 as functions of I1 and I2, right? We did that up here. We can have I1 and I2 as functions of V1 and V2, right? We did that right here. Now, what's to prevent us from saying something else, like I want V1 and I2 as a function of whatever's remaining, right? V2 and say I1, right? And what other combination have I got? I've got V2 and I1 as a function of whatever's missing, V1 and I2. Okay? So you have four variables. You can permute the combinations any way you want. Okay, these others down here are going to lead to what we call hybrid. But really there's nothing hybrid about it. The mathematics is identical to what we did for impedance and admittance. Okay, the only hybrid comes from the fact that what? We're now dealing with one of each, voltage and current, or voltage and current, right? That's the only thing that makes it different. I could actually make it V1 and I1 as a function of V2 and I2, but no, that wouldn't work too good because then I've got solely a function of the output. I don't have the left terminal relating to the right terminal and the right terminal relating to the left. All right, so let's go to our simple network, and we're going to define, or declare I'm going to call it, but define is what's happening, what's known as the hybrid parameters, V1 and I2. Notice on the left, the key thing is you have to pick one variable from each side, from each port, right? That's what's important there, a variable from each port. And that's what I did when I flipped them in the two examples I left at the bottom of the previous page, right? So if you start just with that observation or that definition, you say that V1, what can it be a function of? Once I say, I'm going to write something about this guy right here. All right, I need to pick one input variable, one left side variable, and one right side variable. I can pick two currents, but I already did that, right? That was the impedance parameters. So I only have the choice of this. So that's obviously one of them. And the only other choice is that one. So that's how we end up with I1 and I2. You have to have one from each port. And if the driving variable here is the V, then I have to choose I, right? The reverse is going to happen in the second equation. If the driving variable is I2, then I must pick V2. And then I can have a choice on the other side, but why would I not pick I1? That's just going to make a mess. Well, I can't pick V1 because it's going to be a driving variable. So I'm pretty much, the whole thing gets declared however you want to do it. So this is one of the two forms of the possible hybrid variables. In other words, by hybrid, it's a mixture of voltage and current as the driving variables, namely the variables on the left. Okay? That's what makes it hybrid. But really, the mathematics is just straightforward here. But because the shape of those equations, the structure of those equations is the same as we've been seeing, then clearly there's, oh goodness, I can put this in matrix form. Okay, just like everything else. All right. Now how am I going to find each one of these? I want to know how I'm going to find each one of these. How am I going to find H11? Right? H11 is going to be a function of, well, let's see, what do I want to do? I somehow want to get this term, I want to get H12 to drop out of the equation, right? So using the same technique we did before, we're going to want to set V2 equal to 0, right, is equal to 0. Then I sort of get a freebie that H11 is going to be what? V1 over I1. Okay. Now that H11 looks an awful lot like the impedance parameter. And you say, well, you just defined impedance. But that is not the case, because we did this making V2 0, which means we short-circuited the output. Okay, so that first term, we get this. Now we can keep on going in a similar fashion, right? And we get the next term, H12, right here. We get that guy. So he's going to be what? V1 divided by V2. Those are the two. Where'd my pen go? V1 divided by V2. But now we have to force this term, or this product, to be 0. We have to make that go to 0. And we do that by making, what? I1 equal to 0. And how do we do that? This is open circuit, right? So this is open circuit, and this is short circuit. Okay? And the last two go in the same way that we did before. Again, you're dealing with short circuiting the output and then open circuiting the input. So these parameters, instead of being called literally short circuit or open circuit, they're mixed. Short circuit input impedance. Remember, we talked about that as we did it, so that looks like an impedance. And the dual, the similar thing is going to happen. There's going to be an open circuit output admittance. And now these two terms, we're seeing something that's neither admittance or impedance. We're seeing a gain. And that's because what? We have, this is a current gain, that's a voltage gain. Okay, it's the ratio of voltage in and out, or current in and out. Okay, and notice you have to have a forward or a reverse. This is reverse because it's V1 over V2. Thinking of this as the input and this as the output. Okay, so if something's forward, it's going to be what's the output against the input, and H21 is that. It's the output current versus the input current, so that was a forward gain. Right, so just some terminology, but the important thing is you're then talking about a gain term because it's the ratio of the same value, the same parameter on the, or the same variable on the input and the output. Okay, now the beauty of this, and I'll close with this here, the beauty of this is it leads to this model, and I'm actually calling it a model. So here's our network. I could put the box around all this. Okay. And this model is what we call our basic transistor model, our bipolar junction transistor, BJT. Okay, where there is an input resistance, which we like to be high, so we can keep the current low. There's a bit of feedback voltage, and we tend to know this in transistors to be the turn-on voltage for the diode, right? For the base emitter diode, I'm thinking of you know, the normal configuration, circuit configuration, and then here you've got the collector and the emitter, and you've got a forward current gain, I1 to I2. So there's our forward current gain. We have the dependent source, and this is like the Thevenin impedance here. In fact, both of these, a voltage source and a series resistor, a current source and a parallel resistor, look like Thevenin sources. So a lot of things come together in this model, and this model happens to be extremely useful and directly applicable as a bipolar junction transistor model. Okay, so that's all I'm going to say about the hybrid parameters. We find these, we go through the same process to find them, but in the end you're going to end up with this model of whatever's in the box. And the box may be very complex. You could end up with this same model and it might be a whole battery of transistors. But in the end it gets characterized in this straightforward, simple way. Okay? So that's it for what I'm going to say about hybrid parameters and just parameters, two-port parameters in general.